I guess it's still morning. Good morning. My name's Mike Goff. I'm from Idaho National Laboratory. And I guess I'm the only thing standing between you and lunch now, so we'll see how quickly this goes. In putting this talk together, I kind of wanted to see, what kind of definitions are there out there for pyrochemical processing. So in starting this, I decided to go to the source of all knowledge to see what the definition is. So the first slide there, went to Wikipedia to see what Wikipedia has to... Oh, okay. Oops. So first I went to Wikipedia to see what Wikipedia has to say about pyrochemical processing. And first I was pleased that it is on Wikipedia, and there's a fair amount of information on Wikipedia, and it's actually not that bad of a definition. Some of the key things to note here is, it's still a chemical type process. It takes advantage, it can be a liquid-liquid extraction process, much like the aqueous talks. But the key things to note here that, it typically uses salts, low melting point salts, or metals in a lot of the processing. Actually, I like better the definition that's on the IJCAR, that's the Indira Gandhi Center for Atomic Research. They actually have a fairly good definition, I thought, of pyrochemical processing, and they're actually one of the leaders in doing pyrochemical processing internationally. It's basically, it's high temperature oxidation reduction reactions in non-aqueous media to separate actinides from fission products. And key things to note, it either takes advantage of the volatilities of different elements or chemicals, or it takes advantage of the thermodynamic stabilities of the different compounds to do these separations. And they note in this one, and this is really where most of the pyrochemical processing is going these days, that a lot of it uses electrochemical processes. And that's, again, historically there's been a lot of different type of pyrochemical processing done over the last 40 or so years. A lot of it's now evolved to be electrochemical type processing, again using molten salts and liquid metals. So first, it's probably worth noting, why do people consider different, non-aqueous processes? We've seen a number of nice presentations by Jack and Bob Jubin earlier, talking about there is a lot of experience out there with aqueous technologies. It's applied commercially right now. Works gives you very nice separations, very efficient processes. So why are we looking at other type technologies, and why have people historically looked at some other type technologies? And these are just a few of the reasons that people have in general looked at other type processes. First, it's potentially a fairly compact type process. The advantage in that, and when it was really first deployed, there was the hope that it's compact enough that you can co-locate it with a reactor, depending on what type of technology you use. So maybe you actually have your reactor sites and then one reprocessing plant to handle all the fuel at that site, so you don't have to do a lot of transportation of fissile material around various countries. It's also very resistant to radiation effects, typically. We don't deal with organic solvents, so the solvents that we deal with, molten salts, don't typically have damage from radiolysis. Which, depending on what type fuels you're wanting to process, and especially as we'll talk about more, fast reactor fuels where you're really wanting to reprocess fairly rapidly, that becomes a little bit more of an issue. If you really want to take fuel that's been out of the reactor for only a year or two, you started getting concerned about radiolysis damage to your solvent. So that's a potential benefit. Also, again, if you start talking about especially fast reactor fuels, you start talking about fuels that have fairly high fissile material contents, fairly high concentrations of plutonium or uranium-235. So you like to have a process that has some potential, that has less of a concern about criticality issues, which these dry processes, because they largely don't have moderator present in them, they don't have water present in them, you can actually deal with fairly large quantities of fissile material in the processes. So there's that potential benefit. And as I've alluded to here, that the process in general can be fairly compatible with a lot of advanced fuels out there, especially, say, fast reactor fuels. And we've debated on this last bullet there. There's different people would use different words to explain that. As Bob noted, we don't typically like saying proliferation proof, proliferation resistance, or anything like that, because there is no technology that is proliferation proof. I want to make that clear. Pyroprocessing is not proliferation proof. It may have some pluses, it also may have some negatives and all there. But one of the pluses we generally view is it's capable, it was really designed to produce, most of the technologies in pyrochemical processing were designed to produce low purity products. That is, as Jack noted, aqueous is really set up, it can deal with very high purity products, 4, 5, 9 type purities. This process was developed really to deal with dirty products. Now that's a pro and a con. It was typically the products that you recover, if you want to produce fuel from them, they're usually dirty enough that you actually have to do remote fuel fabrication. You have to do fabrication in a hot cell. So again, some people view that as a benefit, some people view that as a negative, but in general, most of the technologies were set up to produce dirty products. So again, that you maybe have a benefit from a non-proliferation perspective. And like I say, a lot of the work right now, especially in the United States, but in most other countries as well, is really focused on an electrochemical type dry processing right now. But there has been a fair amount of history in other technologies as well, and just wanted to briefly over the next couple of slides mention a few of those as well, just to make sure people are aware electrochemical processing is not the only type of dry processing out there. One that was mentioned in some of at least in Bob's earlier talk, is the vol oxidation process, which goes by a number of trade names depending on how you use that process. DoPick is probably one of the more well-known flow sheets that's been used that has vol oxidation in it. It goes by Volox, Aerox, Deox, a number of different type names. I guess the one thing that I found that every time someone makes a slight modification to the flow sheet, they got to come up with a new name and all, so we continue to rename our very similar technologies. But in general, like I say, as I think Bob noted, basically all that's done in vol oxidation, you're taking advantage of the different volatilities of different elements in fuel. So in the simplest form, what's done in vol oxidation is you take spent fuel, typically light water reactor UO2 fuel, and you heat it to remove the volatile or the gaseous fission products. So in the end, in the simplest case, all you're removing is the noble gases. Depending on what type temperatures you go to, whether you go to, say, 1200 degrees C or not, you can also remove cesium, iodine, and a number of other fission products as well. But in the end, you get still a fairly dirty oxide product after that. So if you apply it to the DoPick process, you could take that dirty oxide product that came out of heating up light water reactor spent fuel, and you could take that fuel, that oxide, and then remotely fabricate fuel and recycle it to a can-do type reactor. So that's the simplest form of the DoPick process, and obviously that's been developed more, especially by the Canadians, and since they developed the can-do reactors, but also the Koreans have done a significant amount of work in that area as well, because they are one of those few countries that have both light water reactors and can-do reactors, so they could deploy a fuel cycle like that in their country. But again, it produces a very dirty product. In fact, that picture down there in the corner there is what happens to the powder after you heat it up. Like I say, when you heat it up, it converts from UO2 to U3O8, which is less dense, so the powder actually expands and breaks up and produces a fairly fine particulate to deal with in the rest of the process. Another sort of gaseous-based process that's been used, and a lot of work has been done, especially at Oak Ridge in this, is halide volatility. And in this type process, you're again, you're taking advantage of different thermodynamic stabilities, but also the different volatilities of different halides of the fission products and the actinides. So in these type situations, you typically convert your uranium fuel over to UF6, uranium hexafluoride, which is gaseous, and you can tend to separate the gaseous fission products and actinides from the non-gaseous ones. And I'll note in this process, this one actually is one of the processes that can actually produce one of the higher purity type products as well. Another process that's been deployed in the past is a process that's generally called partial oxidation, and it's more commonly been referred to as melt refining. And like I say, this process was actually deployed back in the 1960s, from 1965 to 1969, to reprocess fuel from the experimental breeder reactor 2 when it first went operational. In fact, the facility when the reactor was built, it was built with a fuel cycle facility simultaneously, and they used this melt refining process between 1965 and 1969 to reprocess 35,000 fuel elements from EBR2 and remotely fabricate the fuel and put it back into the reactor. And that's where they ran the reactor for its first 5 years of operation. And again, this process is a fairly simple process. In general, what you do is you chop the fuel, remove the cladding, take the fuel material, you would place it into a crucible, and this crucible in this case was made out of zirconium or zirc oxide. You take the fuel in it and heat it up to 1400 degrees C. In doing that, the gaseous fission products are released, and actually most of the active fission products, so things like cesium, strontium, the rare earths, they would actually tend to react with the crucible itself. And they would stay behind in the crucible as a skull on that zirconia crucible, and you could take and then pour out the metal fuel and then use it to refabricate fuel. Like I say, that sounds like a nice, wonderful, simple process, but obviously it had its disadvantages, or otherwise we'd be using it now still too. But in general, the process, it had some disadvantages. It didn't have high recoveries. They could leave, several percent of fissile material behind in that on those skulls as well, and it was a fairly complicated process to recover that fissile material from the skulls. Like I say, it showed that you could reprocess the fuel fairly simply. It also was able to show that you could refabricate the fuel fairly simply. They actually refabricated the fuel using an injection casting process. In fact, one thing that was really nice that they were able to demonstrate from this process, in addition to the co-location concept, that this fuel cycle facility was tied to the reactor, but the one thing that they were really able to demonstrate nicely is they were able to take fuel from the reactor, reprocess it, remotely fabricate material from it, and get it back into the reactor in under 100 days, including all the cooling time. So they would again demonstrate that aspect of the dry processes. But again, they ended up having not as good of recovery fractions that they would like. And like I say, eventually the process was abandoned, and when the decision was made to focus more on oxide type fuels. This was, I guess I didn't note this at the beginning too, this was based using a metal fuel. The experimental breeder reactor 2 operated with a metal fuel throughout its life. And like I said, we'll talk a little bit more about that fuel as we continue on. Now I really want to focus most of the rest of the talk on molten salt electrolysis. And as noted before, everyone likes to rename the process once they start working on it. So really, if you Google search any of these things, really these are all very similar type technologies. Right now, it's more in vogue, we call it electrochemical technology or electrochemical processing, but also, like I say, dry processing, pyroprocessing, pyrochemical processing, pyrometallurgical, and electrometallurgical. And I think I've actually been able to work on the technology throughout all of those name changes, so I guess I've been doing this for too long right now. But like I say, if it does go by a number of names, they're not really all the same, but they actually do tend to apply to the same type technology. So pardon me if I tend to refer to it by different names as we go through this talk. The technology right now, like I say, that's being explored in the U.S. and a number of countries really derived from work that was done back in the 1980s. And the primary two places in the United States that are working on this technology are Argonne National Laboratory in Illinois and Idaho National Laboratory in Idaho. And actually the Idaho portion was Argonne National Lab West when this work was first started back in the 1980s. So like I say, most of the rest of my talk will focus on this specific technology. Okay, some background on it. Like I said, this technology was developed starting in the mid-1980s. Like a lot of good things that come out of the laboratories, it was developed under the LDRD program, the Laboratory Directed Research Initiative program. So it was developed with a fairly small amount of funding, and it evolved into what was called in the 1980s through the 1990s the Integral Fast Reactor Program, or the IFR program. And it's continued in various forms since that time period. And like I say, it really started and was focused on the recycle of fast reactor fuel, especially when it started up in the 1980s. It was focused on taking fast reactor fuel, and very specifically metal fast reactor fuel. So taking metal fast reactor fuel and recycling that and producing a product for going back into a fast reactor. And really, I'd say probably for the first 4 or 5 years, that was its main focus, just the fast reactor fuels. Like I say, and it works very nicely in a fast reactor fuel cycle, because for a fast reactor, you don't have to have a high degree of decontamination of your product. You can deal with a fair amount of fission products going over into a fast reactor as well, because it deals with a fast neutron spectrum. Most of these fission products are not poisons in the fast reactor. So really your product purity in the fast reactor is not governed by the neutron spectrum and the neutronics of the reactor. It's really more governed by compatibility issues with materials. And again, the reasons it was pursued back in that time period, were the same reasons we noted here as well, with the one additional benefit as well that it was looking at, especially with the metal fuels. The metal fuels were found around that time to be able to get very high burnups in reactors. They were able to get burnups. Originally, they had challenges in burnups, but around this time period, they really figured out how you can get very high burnups. The 10 to 20 atom percent burnup range. So you can get as high as, say, 200,000 megawatt days per metric ton. So when they resolved various fuels issues, they wanted to have a technology for recycling those fuels very efficiently. So they looked again at this pyrochemical type process. And like I say, it was very critical in the development early on that it was really integrated with the remote fuel fabrication. So we wanted to be able to develop a process that was amenable to remote fuel fabrication, and a fairly simple remote fuel fabrication process. I know in general, when you think about having to do operations in a hot cell, it's somewhat scary. It's a more complicated operation. You can't touch the equipment. So we wanted to make a process that was a very simple process for remote fuel fabrication. And again, we relied a lot on the technology developed in the 60s to develop a simple process for remote fuel fabrication. In fact, this picture here, this is the furnace that was used to fabricate fuel, and this furnace here, basically in one cycle, can produce 3 fuel assemblies for EBR2, so about almost 200 fuel pins, just using a fairly simple injection casting process. So it's a fairly nice, simple process. And I guess I should point out the picture up here. This picture is the electrofiner that was used in the hot cell for these first operations. We'll have some later discussion about electrorefining in general.
Question, who are some of the commercial entities playing in this arena?
The major one in the United States is General Electric to a large extent. The General Electric Prism design was also a metal fuel fast reactor that was going to use pyroprocessing in it. Now other entities have done some work in it to various extents, but General Electric's probably got the largest name in it. Okay, so I guess this is my slide to talk at least about, to add some chemistry to the talk here, to talk about what's the basis for how pyrochemical processing works. And it's really driven by the stability of the fission products and actinides in chloride media. So this slide here is basically the free energy in kcals per equivalent, or kcals per mole of chlorine, for the different fission products and the actinides. And so the way the process works is these fission products tend to be grouped together and go in processed in a similar manner in the process. Similar, these are grouped together and go into another areas within the process, and then you have all the actinides that basically are lumped together. So what this basically says, if you take spent fuel and you dump it into a chloride salt, these things down on this end of the spectrum tend to like to form chlorides. So if you dump spent fuel into a salt bath, these things will tend to react with the salt and form chlorides and stay in the salt. These things on the other end of the spectrum, if you dump them in the salt bath, they they don't tend to react with the chloride. They're not stable enough, so they'll tend to stay in their zero oxidation state and tend to stay as metals within the spent fuel. And then we tend to use we can use electrochemistry then basically to separate these type items into different process streams. So it's these things in the middle here that we tend to, can tend to manipulate the process in order to be able to recover them. Now, things that like I say, obviously all the actinides are grouped into this region. The other thing that tends to be a challenge is a lot of the rare earths are also grouped into this region here as well. So that poses one of the challenges in making sure that you remove enough of the rare earths in the separations processes. And again, we'll talk about that a little bit more in the future. And a little bit more later on, we'll talk about the waste streams. Where each of these things go with respect to waste disposal depends again on their stability in the overall process as well. This is a very simple cartoon view of the flow sheet for pyrochemical processing. And this one's actually puts up the option of oxide fuel. And let me explain on the oxide fuel side. This process, like I say, it can be modified with head-end operations to take light water reactor oxide fuel, so it's UO2, plutonium dioxide, and fission product oxides. It can be taken to electrochemically reduce that oxide material to a metal state. So reduce the uranium to uranium metal, the plutonium to plutonium metal, and then that material can feed into the standard electrochemical process flow sheet. But it will only result in a product that could go into a fast reactor. This process really is not amenable to taking light water reactor fuel, getting a product, and recycling it back to a light water reactor. It produces too dirty of a product for doing that, and that's aqueous is perfect for doing those type operations. So, like I say, there is a head-end operation that's been demonstrated at the laboratory scale. Just at the laboratory scale, to take commercial oxide fuels, electrochemically reduce it in a molten salt to metal, and then take that material and feed it into the process. So that operation's only been done at a laboratory scale, and that's it for right now. But as we noted in Bob Jubin's talk, pyrochemical processing and aqueous processing, they're not mutually exclusive. You can instead of doing this electrochemical process for reducing the oxides to metal, you could take and use an aqueous process to recover the transuranics from light water reactor fuel and feed that into a pyrochemical process instead. So there's ways to synergistically use the two processes to produce the best overall flow sheet. But again, let me stress, this flow sheet in the electrochemical processing is really focused on recycle a fast reactor fuel or taking feed from a light water reactor fuel and getting it into a fast reactor. It's not for producing thermal reactor fuel for recycle. But let's say the general process is you take the spent fuel, either the oxide from a commercial fuel and reduce it to metal, or you take metal fuel from a fast reactor, you chop it first, place it into an electrorefiner, which is the workhorse for electrochemical processing. And we'll talk more in detail about the electrorefining operation, but in general what you do is through application of potentials to anodes and cathodes, you can tend to recover out the actinide products from this salt system. The actinide products can then go through additional processing in a cathode processor, and you can end up getting a metal product from that you can use for fabricating fuel. And then eventually, though, you have to be able to dispose of your salt, so you can dispose of your salt using some zeolite type material and produce a ceramic type waste. And then you also have to dispose of your cladding and those fission products that stayed in the cladding, and we would tend to do that into metal-based waste form. But we'll go into a little bit more detail on those steps there. Okay, so the electrorefiner. Like I said, the electrorefiner is really the workhorse in the separation process. This is just a schematic of a fairly simple electrorefiner. It's actually the first one that we put into operation in Idaho, where this technology is actually being applied toward the treatment of some of the EBR2 fuel. The specific electrorefiner that we're using one of these electrorefiners. Basically, it's a 1 meter diameter vessel as far as size here. So that's, the vessel itself is 1 meter. It's just a stainless steel vessel. In the vessel, you have a molten salt present. The salt that we use is lithium chloride, potassium chloride eutectic. Melts about 350 degrees centigrade. In that lithium chloride, potassium chloride eutectic, you need to have, you want to be able to transport the actinides. So you need to have some actinides present in that salt as well. We typically will place uranium trichloride in that salt phase as well. So so this electrorefiner typically has about 500 kilograms of salt present in this 1 meter vessel. And of that 500 kilograms of salt, about 30 kilograms of that are actinide, as actinides trichlorides, so as uranium and plutonium trichloride. So in that salt, in that 1 meter vessel. The vessel itself is kept at 500 degrees C. It's always at 500 degrees C. In fact, this specific electrorefiner that you've seen the schematic of here, it's been thermally hot since December of 1994. And we've been using the same salt since December of 1994 in that vessel. And again, the way the process works, the spent fuel, and again, we're talking about metal fuel in this case, so fuel from, say, like the EBR-2 reactor, it's chopped first. And it's typically, unlike a commercial aqueous process where they tend to shear the entire assemblies at one time, we tend to chop more like 4 pins at a time. So you chop the fuel and take those individual chop segments and you place them into this steel basket here. For reference, this steel basket's about 9 inches in diameter and about 12 inches in length. In one of these baskets, you can chop 12 kilograms heavy metal, so 12 kilograms uranium, from fuel from EBR-2. So that actually turns out to be 3 EBR-2 fuel assemblies. So you chop that fuel, place the fuel segments in this stainless steel cruciform shaped basket. That basket is then lowered into the molten salt, into the electrorefiner, so it's basically depicted here in this purple. So it's lowered into the salt. Then you also have in another port, you can lower in a bare steel mandrel. And then you configure these so that the basket is an anode and the bare steel mandrel is a cathode. You apply a potential between the two and you anodically dissolve the fuel out of the cladding. So the uranium metal in the fuel becomes oxidized to uranium trichloride, and simultaneously at the cathode, uranium is reduced from the salt. And it's reduced and deposited, like this dendritic picture here, in a dendritic form on that bare steel mandrel. This is about a 10 kilogram heavy metal deposit on, again, the bare steel mandrel. So you're recovering the uranium out in a relatively pure on a bare steel mandrel. In that process, as we'll probably talk about in a couple other slides, the fission products that form stable chlorides, so cesium, strontium, the rare earth fission products, lanthanum, neodymium, those all form chlorides as well. So they get oxidized and go into the salt. So those fission products build up into the salt phase. The plutonium, especially the plutonium trichloride, is more stable than uranium trichloride. So it actually tends to build up in the salt phase. And one of the challenges, I think as Bob noted, we hadn't done a lot of engineering scale work on recovery of transuranics. That is one of the challenges, is how you recover the plutonium and the minor actinides. Like I say, uranium deposits out very nicely on these bare steel mandrels, so that's how we recover those. But I'll talk a little bit more about transuranic recovery.
This is a batch, and you have to cool down to go get your uranium off your cathode. Yeah.
When you pull the cathode out of the electrorefiner, it cools down. You never cool down the electrorefiner.
Salt stays molten.
Salt stays molten the whole time. But like I say, but that's a very good segue to the next slide. Yeah, when you pull out that uranium cathode, so it was in the salt at 500 degrees C. You pulled it out into the cell atmosphere that's about 100 degrees F. The salt freezes, and it adheres to that cathode. So it turns out that cathode now will probably have, it was about 10 kilograms of uranium on it, but it also probably has about 15% weight salt from the electrorefiner adhering to it. So the next step is you've got to be able to separate that salt from the uranium product.
I have a quick question.
Oh, yes, Melissa.
So the mark for electro-refiner, is that the same thing as the melt refining furnace that was depicted on your previous slide?
How far? So how many? So this.
Back.
Yeah. Go, if you can go back.
You can't. Here, I'll handle it.
Okay.
The clicker doesn't go back.
Okay. So one more to. On this one or on that previous?
On slide 6,
No, then it wasn't on that one.
that melt refining furnace, is that?
That one was. It serves as in the melt refining process. That served to do the bulk of the separations. But melt refining wasn't an electrochemical. It was not an electrochemical process. It was just a pure chemical process. So it was a different furnace. Okay. Actually, so I can answer your question, why don't we go forward one more and then we'll stop there and then we'll come back to that other one. Okay, so we've taken that uranium out, and yeah, you're right. So once it comes out of the electrofiner, it's cooled down. So what you need to do is you need to be able to separate the salt from the uranium metal. And we do that basically in a retort process. Well, first you have to take the uranium off that bare steel mandrel. And since you asked, I'll point that one out. The way they do that is they put a die plate around the top of the mandrel and lift up the mandrel, and the dendrites just fall off. The dendrites are pretty easy to just physically scrape off. And they fall off and placed into a crucible. These are graphite crucibles. So they go into this crucible, then we place it into a retort furnace. That's basically the furnace will heat them up to about 1200 degrees C under vacuum. You distill off the salt. The salt gets collected down into a bottom receiver crucible, and then that salt gets recycled back to the electrofiner. The uranium then gets melted into an ingot that can be used for whatever you want to do with the recycled material. So yeah, you do have to do that operation. And you also have to do that from, say, if your cladding hulls, when you've taken them out of the salt as well, they've got salt adhering to them, you've got to distill that off as well. So that's all done in the cathode processor. And again, it's an induction heated furnace. And again, we use graphite crucibles, though in this case, this bell jar is a susceptor instead of the graphite crucibles. But, okay, so now if we want to go back one slide. Okay, so we also talked about the transuranics. The transuranics are more of a challenge to recover. And it's basically, again, driven by the thermodynamics. Plutonium trichloride is significantly more stable than uranium trichloride. So plutonium will not tend to deposit on a bare steel mandrel unless there's no uranium around. And even when there's no uranium around, it tends to froth off instead of forming dendrites. So if you want to be able, you've got to use some tricks of chemistry in order to get them to recover the transuranics well. And basically what we've come up with for transuranic recovery is what we call a liquid cadmium cathode. So instead of having a bare steel mandrel being your cathode, we use a pool of cadmium. So this is a ceramic crucible, and inside the crucible is about 26 kilograms of cadmium. And you make contact with an electrical probe that's insulated to the cadmium surface so that when you apply a potential, the surface of the cadmium becomes the cathode. And so now you're depositing in cadmium instead of on stainless steel. And it turns out the plutonium and the minor actinides actually have a very low activity coefficient in cadmium, and they tend to want to deposit into cadmium. Much so that even though you don't have even though you still have a lot of uranium in the salt, the plutonium and the minor actinides will be recovered as a group in a liquid cadmium cathode. So the way we recover the transuranics, we don't tend to recover just plutonium. We recover plutonium with the minor actinides, so with americium, curium, and neptunium, and some amount of uranium as well. We have done this on an engineering scale, and by engineering scale, we talk about recovering greater than a kilogram of transuranics in a single time. So we've done a limited number of tests with this to demonstrate that the technology works. But as Bob noted, more work's needed in this area to really demonstrate you've got a commercial process. But like I say, it has worked fairly effectively for demonstrations of the recovery of the transuranics and demonstrating that you can recover all the transuranics as a group. Because that's one of the things that we've strived to do is recover them as a group. We don't want to have separate streams of the transuranics. We want them all together. Now, the other challenge we'll note in this too is, as we showed in that earlier slide talking about the free energies of formation, the rare earth fission products also behave a lot like the transuranics. So you will get fission products recovered with the transuranics as well. So one of the challenges is to make sure you don't get too many fission products, because one limit that you do have is a material compatibility issue. That you are concerned about getting too many rare earths coming over into your final fuel form, because the rare earths will tend to form low melting point eutectics with stainless steel cladding. So you've got to make sure that you don't get too many over there, or you'll end up having fuel cladding interaction problems. Okay, so we already covered the cathode processing. And now maybe at least talk a little bit about background on how the technology has been used and some of the things on the status of where we've gotten to with different parts of the technology. Like I say, the technology was started under the Integral Fast Reactor program, or the IFR program. That program was terminated in 1994 when the Department of Energy terminated all work in fast reactors. So EBR-2 was actually shut down and the IFR program was terminated. At that point, the fuel conditioning facility that was used earlier for that melt refining demonstration had been modified to demonstrate the electrochemical recycling, but the program was terminated before that demonstration occurred. But at that point, when the reactor was shut down, there was a decision made that we needed to be able to treat the fuel from EBR-2 for disposal. So the Department of Energy decided they wanted to assess the technology for treating the fuel for disposal. And the way they went about, well, and I should note what the fuel from EBR-2 was. Again, it was a metal fuel. The driver fuel was highly enriched uranium fuel, so about between 53 and 78% enriched, but most of it was around 63% enriched after irradiation. There was also a fair amount of blanket fuel as well. EBR-2 did originally operate as a breeder reactor, but after they demonstrated the breeding concept, the blanket was just left in for shielding to protect the pressure vessel. But it stayed in the reactor for its entire life, so there was a fair amount of plutonium that got bred in the blanket. So there was fuel left from EBR-2 that needed to be treated. The one thing that's very unique about the metal fuel is typically sodium is added to the fuel element itself. A bit of sodium is placed into each individual fuel element in order to provide a good thermal bond. Since a lot of people here have worked at Yucca Mountain, in general in Yucca Mountain we were trying to make sure we didn't put any kind of hazardous waste into Yucca Mountain, so there was a concern that sodium bonded fuel could not be directly disposed of in Yucca Mountain. So the department decided to use the technology for treating the fuel for disposal. Before they did that, they set up a subcommittee of the National Research Council to review the technology and review a demonstration of it. They also did a non-proliferation assessment, an economic assessment. In the end, the National Research Council found that we were able to meet all of our criteria to demonstrate the feasibility of the process. They did an EIS, and in 2000, the technology was moved forward for treating the fuel for disposal. So like I say, so it went from the IFR program in 94 to being redirected to treating fuel for disposal. Like I say, that change occurred in 94. They formally finished the demonstration, though, in 2000, and the decision was made to go full scale toward treating the fuel in 2000, and continued in that mode until the Advanced Fuel Cycle Initiative was formed in 2002. At that point, the department made the decision we could look at recycle technologies again. So we did start again looking at electrochemical processing as a recycle technology while simultaneously treating the fuel for disposal. So we started again looking at transuranic recovery and those type of things starting in 2002, and that was when we were able to do a demonstration of that liquid cadmium cathode technology. I guess I should also go back to, from a liquid cadmium cathode, we talked about you recover the transuranics in this pool of cadmium. you've also got the challenge, what do you do with that cadmium afterwards? And we do remove that by a distillation operation as well. Cadmium boils at a fairly low temperature, so you can boil the cadmium off, and then you're left with just a transuranic ingot for recycle. So like I say, the technology right now is still being applied toward treatment of EBR2 fuel and some fuel from the Fast Flux test facility. But it's also being looked at as far as demonstrating different gaps associated with the recycle technology as well. As far as type facilities where this work is done, the key difference in where this work's done as opposed to an aqueous or reprocessing canyon is really a lot of the cell atmosphere. Right now, the two facilities we use are the fuel conditioning facility and the hot fuel examination facility in Idaho. Those hot cells are inerted hot cells, so you don't do this processing in air. The salts are typically, will pick up moisture. Metal fuels tend to like to react. Sodium definitely likes to react, so we tend to use inerted hot cells. So they're hot cells filled with argon gas. And like I said, we do have two of those operating in Idaho, the first being the fuel conditioning facility. And this is where we do all of the process type operations. And then we also have the hot fuel examination facility, which is where we produce high-level waste from pyrochemical processing. And I'll talk about the waste work in a little bit further on. And I'll note, the fuel conditioning facility is the same facility that was used for the melt refining process back in the 1960s. After several upgrades on the facility, though. So the key difference in what's being done with the process right now in Idaho compared to that first flow sheet that I showed you is we're not recovering transuranics. We're retreating the fuel right now for disposal. And we're doing that in two different electrorefiners. We have two process lines in the fuel conditioning facility right now for processing fuel. We have one process line that's used for processing the driver fuel that's highly enriched, so it has its own chopper and electrorefiner, and another process line that's used for processing blanket fuel, which again is more depleted uranium but also has a reasonable bit of plutonium associated with it as well. So those two electrorefiners, from those you recover different uranium products, and they go through a single cathode processor to distill off the salt and have a recovered ingot that's then taken and cast. Pin samples are taken, and right now it's stored out of the hot cell. So like I said, we have these two process lines going right now in the facility. We use the equipment, though, to demonstrate other aspects like transuranic recovery as well.
And where's the fuel coming from?
From the from EBR2.
Okay.
From EBR2, and we did start last year processing some sodium bonded metal fuel from the Fast Flux test facility as well. To date, this process has been used to treat about 4.5 metric tons of heavy metal, again from EBR2 and the Fast Flux test facility. Like I say, some of that's a mix, about a little over a ton or so of that's highly enriched material. The other is the blanket material. In the facility that we have right now, if we were staffed at a 7 days a week, 24-hour a day staffing, the facility size to be able to handle about 3 to 5 tons per year. Say right now our focus has been more on R&D and not on throughput necessarily. But like I said, the products that are recovered are stored out of cell just in racks. So that is one of the uranium products after processing. It's about a 60 kilogram ingot, I think. One thing that is brought up about the technology, as you've noted probably, it's a batch process. This is not a continuous type process. We don't have a continuous dissolver. We don't get to use centrifugal contactors like Jack talked about. We do deal in a batch process. Though I will note, we did make pyro contactors at one point for testing, which that was really interesting, having contactors that can handle a 500C environment, pumping molten cadmium. But that, like I say, we have a few of those around. But again, it is a batch process. So one thing that you're concerned about with batch process is scalability. So it's something we've been focusing on. How do you scale up the technology, and how much have we scaled up the technology? So we did look, a few years back to see, well, how far have we scaled it so far in the hot cell? We've had 3 different electrorefiners that we've operated in the hot cell. Two of them, well, actually all three of them are still operating, but two of them are the workhorses for processing the fuel right now. This first one is what we call the hot fuel dissolution apparatus. It was used for all of our process testing. So it did look at between those three electrorefiners. It turns out, yeah, we have scaled the process by 3 orders of magnitude in the hot cell between those 3 vessels. The thing that I actually found more impressive, though, when I started looking at it, is between our Mark IV electrorefiner, so the electrorefiner we use for processing driver fuel versus the one we use for blanket fuel. Those 2 vessels are identical footprints. They are, in fact, the vessel that we use for the Mark V electrorefiner that processes blanket fuel was the backup vessel when we built the first one. So between those 2 electrorefiners, by a change in the anode-cathode configuration, we're actually able to increase the throughput by a factor of 20 in the same footprint. And actually that was done over about a 2-year period. And so like I said, the technology appears to be scalable. Now what its upper limit is, we still haven't found out what that is yet. But we will have much bigger challenges to try to design a 1,000-ton per year facility like Jack was talking about with this technology compared to other technologies. When you ask the question about commercial type facilities, so if the type scale that we're talking about with this technology and like what GE was talking about when they started looking at PRISM, if you took their PRISM reactor and you produced a power park that say produces a gigawatt of electricity using PRISM reactors, the fuel conditioning facility that we're using now is roughly, within a factor of 2, about the size that you would need for that power park. So again, we wouldn't necessarily look at scaling the technology up much larger than this, unless you go into, like say, the treatment of oxide type fuels. As far as some of the advancements that have been made in the technology since we started looking again, focusing on it as a recycle technology as opposed to just a disposal technology. Like I said, we have been able to demonstrate that we can do group recovery of the transuranic products at a kilogram scale using that liquid cadmium cathode, and that is one of those ingots after the cadmium's been distilled from it. So this product here actually has a little more than a kilogram of plutonium and also minor actinides and uranium present in it as well. So we've been able to demonstrate that on a limited number of tests at the engineering scale. But again, not demonstrated that it's ready for commercial processing. We've also been able to demonstrate that we can get a good dissolution efficiency of the actinides from the spent fuel. Again, if you're starting looking at wanting to reprocess to obtain benefits from a waste disposal perspective, you want a greater than a 99% kind of recovery of the actinides from the spent fuel. So we have demonstrated, we've been able to get routinely in our operations 99.7% dissolution of the actinides from the process. So that's the average from all the runs that we've done at the engineering scale. Okay. We've been able to demonstrate we can reprocess the feed material. The metal fuel typically is alloyed with something like zirconium. We've demonstrated we can recover and recycle that zirconium as well. We demonstrated we can make some fairly nice crucibles for casting this. These high temperature processes, one thing you're always concerned about is dross formation and crucibles and materials of construction, so we've done a lot of work in that area as well. And also, like I said, there's been a lot of work done in the fuels area too to be able to make sure that we can produce fuels from this well, again using the ejection casting process. I don't think I'll go into that too much here because I want to talk briefly about the waste. We've demonstrated, again, on the laboratory scale, and by lab scale I mean like 40 gram of heavy metal, that you can take oxide fuel from light water reactor, reduce it to a metal, and then electrorefine it. So we've demonstrated that with irradiated material on the laboratory scale, but we haven't gone above that at this point in time. And we've done some feasibility work and some conceptual design work on some larger scale facilities, like a 100-ton type facility for doing that operation. Again, now just to briefly talk about the waste, we do have 2 different waste forms, and the waste forms, one stabilizes the fission products that go into the salt. The other stabilizes the fission products that stay behind in the cladding halls. So for the salts, we stabilize them in a zeolite-based waste form. Actually, we'll take zeolite and convert it over to sodalite. The the noble metals that stay behind in the cladding halls, we actually melt them with the cladding halls and some zirconium to produce a low melting point stainless steel zirconium ingot, eutectic that actually, again, stabilizes those fission products fairly nicely. John, I don't know if you're talking much about these waste. You're going to cover some of those as well. Like I said, we have the engineering scale equipment installed for producing the ceramic waste form all in the hot cell except for the production furnace. We have not put a production furnace for producing that waste form in the cell yet because we don't have to dispose of our salt yet, so there's no driver for us to install that and take up footprint in the hot cell yet. But like I said, we have demonstrated that overall process. And again, we're trying to produce a waste form that's very similar in size to the glass produced from, say, Savannah River or eventually Hanford's. So roughly getting around a 19 or 20 inch ingot they're going to be shorter than glass, but around 300 kilogram type ingots.
You're staying dry through that zeolite process.
That's right.
Okay.
Yeah, in fact, the first step with the zeolite is you may be aware, zeolite picks up moisture very readily. So the first step we have with zeolite is going through a drying operation on that.
Is that a natural zeolite?
We buy a commercially available zeolite from UOP. It's 4A. But we then convert it over to sodalite, and the reason we chose sodalite is because sodalite is one of the few things that naturally occurs that retains the sodium chloride in it nicely.
Okay.
The other waste form is the metal waste, and again, it's more simple. You got the cladding hulls that come out of the electric refiner. They tend to have the noble metal fission products still staying with them in the cladding hulls. The cladding in this case is stainless steel. We go to a single furnace that'll go through and both distill the salt that adheres to the cladding hulls because they came out of the electric refiner. It distills the salt first and then melts at around 1600 degrees C the stainless steel and zirconium noble metal mixture into an ingot, again for disposal in a potential repository like Yucca Mountain or something. I think the final thing I want to mention, other countries. There are a number of other countries that do work in this area. Just noted here, I think when we put the slide together, we had recently, at the time we first put this together, we had a pyroprocessing conference. At that conference, there were about 7 countries that were represented from around the world that are doing significant amount of work in that area, about 70 presentations. So this is just presentations on pyroprocessing of used fuel. Since the one that we hosted in the United States, there's been a follow-on conference in Korea and Russia, and I believe the next one's supposed to be in India. But like I said, these are some of the countries that are the leaders also in this technology. The Republic of Korea, Japan, India, Russia. Russia uses a different type process, but still an electrochemical based process. And then, like I said, the Indians are becoming much more active in this area. So really, that's pretty much it. So, any questions?
I got a general question. The light water reactor fuel, uranium enrichment is between 3 to 5%. After all this chopping it and beating it, all this processing, does the enrichment level change?
No. No, it doesn't do anything to affect the enrichment level.
So, thinking back to the operations again, I mean, since all this is done in a hot cell, what if something goes wrong with the process when you're in there? Like malfunctions and that sort of thing. I mean, it just seems like this would be a giant nightmare to fix.
We've been operating it now for 16 years? No, 17 years. I mean, the one thing that you find, the people that design equipment for hot cells, it's a separate breed of person. It's not your standard mechanical engineer, and you don't find them much anymore. I mean, a remote design engineer is really very much an art type design. So they build the equipment with enough redundancy that you can handle a lot of different type failures. Now, and that was a challenge with this equipment because this equipment was first of a kind. So they had to design redundancies on things you didn't know, what were going to happen, what are the type failures that you can have happen. But like I say, all the equipment's designed so that it can be repaired remotely, can be transferred in and out of the cell remotely. In fact, all the equipment that was in the cell there was installed remotely because that cell was already a hot cell and had gone through hot operation. So the electric refiners, all the cabling was all installed remotely. It's just part of the design. You've got to design it in for any of those type repairs. And we've had a few things that were unexpected. One thing that actually was probably the funnest thing that we did, when I was working on this project was we had an electric refiner cool down, and the whole 500 kilograms of salt froze. It was something we thought could happen, but thought it was way down on the priorities. But we were able to actually remelt the system in less than a week and get it back up and running because there was enough. The heaters were designed in such a way that were set up that we knew this could happen, and you could heat in a certain manner so that the salt wouldn't expand. But like I say, you've got to design equipment in any of the hot cells well so they can come out. If it is something that you think is going to fail, it's got to be able to come out and be replaced fairly easily. Quick disconnects and stuff like that.
What's your life on those?
We don't know. Again, because these are the first of a kind. What's the lifetime on the electric refiners? Because of the first of a kind piece of equipment, what we did do with them, we put a number of different corrosion coupons in the first vessel, and we've been pulling them out periodically to see what kind of corrosion rates we are getting on them, so we can start looking at what the what concerns we have. So far, we haven't detected any corrosion on them. The things that we're finding that's going to be more not life-limiting for the whole vessel, but the things we're going to have to change out first are the things you probably expected, the electronics. The cabling is probably one of those things that at some point in the next 5 or 10 years we'll have to replace the cabling because it starts getting brittle. But we have been real pleased on the vessels. Like I said, we probably thought we would get some type of corrosion. We do keep a very high purity atmosphere on the interior of that vessel as well. Those cells are typically kept at 50 parts per million moisture and oxygen in the cell itself. The vessels are usually around 1 to 2%, 1 to 2 ppm moisture and oxygen, so the corrosion's been very low on them so far.
You're pretty much a clean room operation.
Not if you looked in the cell, you wouldn't think. Yeah, because you got junk all. But you keep the atmosphere very, and like I said, the salts are corrosive, but they're only corrosive if you have moisture in the system. But that's something we're monitoring.